Yeah, so this lecture is going to be relatively short, and then we'll come back next lecture and then solve bunch of problems and then kind of more or less remind ourselves where we have been so far in the course, right? So we have seen essentially bunch of results on how to prove a solution or a system to have some desired behavior. Specifically, we defined Lyapunov stability, asymptotic stability, and of course, we saw this wonderful theorem by LaSalle or Barbachan, Krasowski, LaSalle, which helps further in terms of showing some kind of convergence, and then we can also use it for showing asymptotic stability and things like that. And all these things rely on one single thing, finding that function that we call as Lyapunov function candidate or Lyapunov function if it satisfies all the conditions, and then depending on situation we can prove asymptotic stability using directly the Lyapunov's theorem. If you have a strict inequality, whereas in the case of LaSalle you have to go through this subtle argument coming from invariant set theorems, right? Now, one of the questions is, are we always confident in terms of finding Lyapunov functions? The answer is, it's not easy to find them, but at least we should be supported by some theoretical results that we can actually always find one. It's just that it may not be easy to find one, right? But of course, in addition to say suppose we are unable to show something is stable, but if we can show somehow something is unstable, that is good enough. I mean, that means our search for stability is obviously pointless at that time. So to support all these things, there are a couple of results on instability, right? And these things are because of the fact that converse is more theoretical nature. It's basically knowing that we have a way of somehow convincing ourselves there is always a function. Instability is more a negative result. So these are not the most popular results in that sense, right? So therefore, I'm going to just state the results and not really go into the proof of it or anything like that. So as usual, we have this ODE f x dot equals f of x, and then we assume f of 0 is 0, so that the 0 solution is defined, right? But here we make the assumption that 0 is asymptotically stable, okay? And the theorem will eventually conclude, but basically let's since it's asymptotically stable, that means there should be a region of attraction. What is the region of attraction? Let's remind ourselves all the points from which this particular system will be such that the trajectories are going to go to reach the equilibrium point, the asymptotically stable equilibrium point, in this particular case 0, right? There could be other equilibrium points somewhere else far off from 0, but close to 0 there should be a region of attraction which will attract all the solutions will converge to 0, right? So in that region, and then we haven't really paid attention, but if you don't have a continuous set of equilibrium starting from 0, you can actually show that there is going to be this region of attraction is going to be an open set. And therefore we can actually find a ball around the 0, right? So pick some ball, right? And the theorem says there exists a continuously differentiable function v such that v of 0 is 0, v of x is positive for x non-zero. I don't say it explicitly. Yeah, I do at the end. And also v prime of x times f of x is strictly less than 0 on the entire ball that we are talking about, without of course the origin, right? So if you notice, there's not much to say. It basically says that we can find a Lyapunov function if we know somehow this particular origin happens to be asymptotically stable, and that's a good thing to know, right? Please notice that this Converse theorem starts with asymptotic stability and not Lyapunov stability, so which indicates that basically finding Lyapunov stability, finding Lyapunov function for Lyapunov stability is not guaranteed through any Converse theorem at this point, right? There are some generalizations which we don't consider, but the more interesting case is anyway asymptotic stability. So, we have guarantee from theory, basically if we have a asymptotically stable origin, then basically you will have a Lyapunov function locally. So, and one can think of a similar result that is extended to exponential stability. So, the same kind of assumptions. You have this ODE, and the zero solution is assumed to be exponentially stable. Once again, if it is exponentially stable, that means it's asymptotically stable. So, there will be a region of attraction, and within that region of attraction, we are going to pick a ball. And we are not going to pick a ball. Actually, the statement should be very clear. There exists a continuously differentiable function such that you will find a delta on which these conditions are satisfied. Same thing is true about the asymptotic stability also. On a small ball, we can certainly show that this function exists. In the case of exponential stability, not only can we show that v of x is positive definite and things like that, but much more. V of x is actually lower and upper bounded by these norms. There is a more general result where you take any norm of the vector and then power p and things like that, where p is greater than 1. But I chose to just simplify the presentation and put the simplest possible result that I understand. So, v of x is lower and upper bounded by these squares of norms, right? Some scale version of some scalar multiple of these squares of norms, and v dot is going to be less than or equal to minus epsilon times v of x. So, if you recall, these are the sufficient conditions for exponential stability, right? And of course, clearly this indicates asymptotic stability. I don't have to mention that again and again, that exponential stability implies asymptotic stability, right? So, we will eventually end up with basically the next result that says if you have globally exponentially stable equilibrium, right, the origin in this particular case. Of course, when we say something about global, that means that's the only equilibrium point. So, we don't have to worry about these deltas and things like that. The only assumption we have to make is basically f is continuously differentiable and globally Lipschitz, and these are the type of conditions we anyway require for existence of solution from 0 to infinity, right. So, these are the basic assumptions, and then basically the conclusion is very straightforward, right. It's the same condition that we saw, except these conditions have to be true throughout the space Rn. Right. So, we have these three results: asymptotic stability, exponential stability, and global exponential stability. Whatever is missing, basically, Lyapunov stability or global asymptotic stability, they are not either easy to show, or they don't exist for the simple case we are looking for. There are many results when we go to time varying systems and things like that. There are many more results in the Converse section, right. So, it's good to know. It's good to know that these most of the systems that are interesting, we want to show global exponential stability. So, if somehow we figure out that there is a exponentially stable point, then we have this function. So, searching for v is therefore is not in vain, right. That's the point we are trying to make. So, because the problem with sufficient conditions is it's possible that the system could be the zero could be globally exponentially stable, but there is no Lyapunov function, in which case we can never search for it, and then we can never find it, right. So, therefore, searching for a Lyapunov function is going to be a little bit more adventurous at that time. But on the other hand, Converse theorems suggest that there is guarantee of finding such a Lyapunov function, and therefore, it's not a wasted effort, right. So, let us actually consider how this works in the linear case. I am not trying to show any of these proofs, but a linear case will help us, right. So, let me go back to this other software Nebo to fill in the gaps, right. So, basically this in this example, what we are going to see is, well, first thing I want to point out is basically The proof of converse theorems basically rely on constructing some v of x as some kind of integral between 0 and infinity of some kind of function some function in gamma is k class, etc. So there's some complicated versions. I'm not trying to provide details. Some kind of assumption made on this gamma, some kind of interesting function, whereas what we see inside is basically the flow, right? And when we integrate it out, t will disappear and we'll have a x, right, of a function of x. So imagine the nightmare in terms of trying to actually figure out this function using the proof of converse theorem. But luckily, in the case of linear systems, we can think of this function as gamma as basically something very simple, and then so we're going to say S transpose x times S of t comma x is your so gamma is essentially is u transpose u, right. So since for linear systems we know the solution, right. So this is going to be essentially x transpose e power a transpose t and then e power a t x dt. Since this integral does not depend on x, so I'm going to isolate just the t part. We'll have this, and then let me define. I mean, as you can see, once this integrates it out, basically you'll end up with matrix, right, square matrix specifically, and let me call that as P. Okay, so what can we say about this P? Perhaps I should go to a different page. So P is equal to integral 0 to infinity e power a transpose t e power a t dt. Okay. One of the things that we can think of doing is basically multiply a transpose in front, and you will get a times e transpose t a t dt, and then you can actually add post multiply p and then add the other side to it, and everything becomes symmetric at that point, right. And remember, a commutes with exponential, so all these things are nice, right. So it's a nice observation. Basically you will get d by dt of essentially e power a transpose t e power a t dt. Okay. So that's what this is. If you recall some of the algebra that I showed during matrix exponential this thing. So when we integrate it out, one of the nice things about this entire thing is the question is basically when we define this v as, if you recall, v as S transpose S integral, the first question that should come into our mind is basically whether this particular integral exists or not. The fact that this is linear system is asymptotically stable, which is equivalently exponentially stable. We'll look at some of those details later. So this S square actually exists. Similarly, this e power a exponential of a transpose t and times e power a t, therefore has to exist, and then that is what we are looking at it, right. So when we integrate this, we will essentially get e power a transpose t e power a t between 0 and infinity. The nice thing is basically as t tends to infinity, since this is exponentially stable, this goes to 0, right. I mean, so at infinity that part is going to be 0. At 0, time is equal to 0, this becomes identity. So I'm going to get minus identity. So what did I prove? I proved that a transpose p plus pa plus identity is equal to 0, right. So, by the way, not surprisingly, this is called Lyapunov equation. Okay. To be specific, it's called matrix Lyapunov equation. So, what did we show so far? I started with V. I suggested that basically the Converse Lyapunov theorems use this trick that to construct V of x, it does some integral, and that ends up being x transpose px. So, in linear case, we actually show that V of x can be chosen to be quadratic by choosing this very specific integral and things like that. But much more than that, this p satisfies this nice Lyapunov equation. Now, remember x dot is equal to ax. So, I am going to take the derivative, Lyapunov derivative. I am going to, hopefully you know how to take these derivatives. X dot transpose px plus x transpose px dot, right? And that's going to give me x transpose a transpose p x plus x transpose p times ax, which is simply x transpose times a transpose p plus pa times x, which of course we know that minus x transpose x, which is strictly less than 0, right. So, therefore, we conclude that the system is asymptotically stable. I mean, the conclusion is not important because we started with the assumption that it is asymptotically, globally asymptotically stable, but the fact that it's checking out, right. I did get a Lyapunov function that satisfies all the conditions that we have in the typical Lyapunov function. Okay, so that's just an insight in terms of this Converse Lyapunov function theorem, right. So, similarly, there are a bunch of instability theorems. So, the instability theorems, Lyapunov gave a couple of them, and then there's one more scientist called Chataev. There's a result based on his name. They are a bit fussy, but not too complicated. So, we start with some kind of assumption of existence of V and some epsilon positive constant such that V of 0, 0, we dot is greater than 0 on this ball without the origin, and furthermore we have to make this assumption that basically V is actually close to delta, close to the origin. We can find V to be positive definite. Then we conclude that the 0 solution is unstable, right. So, what is the difference between standard stability result and this one? Well, obviously the sign that we have on the V dot, right, and a couple of other things, but essentially we are showing somehow that we are going to get away from the origin if you perturb a little, right. And if you do this example, one will realize that basically all the conditions will be trivially satisfied when you actually take V dot. You can find one point where this is going to be positive. So, I'll leave that as a homework, and then perhaps we can try to solve this in the next solved problems, right. So, similarly, Lyapunov gave a second instability theorem, looks slightly different, but it is essentially saying the same thing. V dot is going to be somehow positive because Wx is some non-negative function. V is anyway known to be some positive around the origin. I mean, that's the next assumption. So, using all these things, we can actually prove that this point is going to be unstable, and one can try this particular example, again satisfying all those things in this example in such a way that V dot is going to be exactly equal to lambda, some lambda times V of x plus W of x, right, where W of x is non-negative. Again, I'll leave it as homework for now and then come back and show probably how to do this in the next lecture, right. The last one is a bit more fussy in terms of the way it's stated and things like that. I'm just going to state it and leave it at that. So, again, we are looking for some function V and things like that, but there's this open set Q such that the boundary of this open set contains 0, not Q itself, but the boundary, It's a very strange, imagine basically some open set touching 0 and then just going away, but it's still a subset of some ball around epsilon and satisfying all these conditions. Again, the common thing is basically this V dot is going to be positive, but this time on this open set Q, then we can show 0 solution is unstable. And each of these results can be attempted to show instability, right? Again, the summary is very straightforward. This particular lecture basically trying to show that first, if somehow the equilibrium point is known to be asymptotically stable or exponentially stable or globally exponentially stable, then looking for a Lyapunov function is not in vain. I mean, we can certainly find it. Finding it is probably not that easy, but still, you're not just trying to imagine that there is one, right? So with that, we'll end this particular lecture today, and then come back and then have a longer lecture composing bunch of solved problems. So you can look at it one problem at a time. We'll look at some of the very basic issues like how to show continuity, because anybody who is trying to solve nonlinear systems should understand. Yeah, so we will solve bunch of solved problems next time we see. Thank you.